Good afternoon. Good morning, everybody. I'm Renee Yager. I'm the Director of Marketing at EPC, and welcome to today's webinar. Before we get started, just a few housekeeping items. You can submit your text questions to the panel by typing your questions into the Q&A feature at the bottom of your screen, and you can send those in at any time during the presentation. We'll collect them and address them during the Q&A session at the end of today's presentation. So I will introduce you today to our panelists. First up, we have our speaker. It's Tiziano Morgante. Tiziano is EPC's Senior Field Application Engineer for EMEA. He has over 20 years in the power electronics industry. Tiziano has held roles as an electronic design engineer, electrical engineering team leader, system design engineer, and GaN hemp-based inverter concept and design leader of a 2-kilowatt inverter submitted to the Google Little Box Challenge competition. Also joining us on the panel is Rolf Horn, Enhanced Advanced Applications Engineer at DigiKey Electronics, Germany. Rolf has been in the European Technical Support Group since May of 2014, with primary responsibility for answering any development and engineering related questions from customers in EMEA, as well as writing and proofreading German articles and blogs on DigiKey's Tech Forum and Maker.io platforms. Prior to DigiKey, Rolf worked at several manufacturers in the semiconductor area with focus on embedded FPGA, microcontroller, and processor systems for industrial and automotive applications. Thank you, everybody, for joining us today. And Tiziano, you can get started when you're ready. Thank you.
Hey, welcome to the webinar. So in this webinar, we will cover the following topics. So basically, we will start about talking about the inductances in a circuit and their impact on the switching behavior and switching losses. We will describe a few different design options for the layout of an half-bridge power circuit. We will provide guidance how to design a low inductance layout. We will focus also on the gate drive layout. We will show some common mistakes and how to fix them. We will cover an example discussing how to parallel GaN FETs for higher current design. Then we will cover what are the properties of the PCB design and which requirements are needed for laying out an EPC GaN FET on a proper PCB. And then we will discuss the difference between the layout for a motor drive and for a DC-DC converter. So let's start about the inductances. So this is an exemplary half-bridge circuit. So we have the power devices, the bypass capacitor, and the gate driver, together with the bypass capacitors for the gate driver and the gate resistors. So the first inductance we are talking about is the common source inductance. This is shared between the power circuit and the gate circuit. Then we have the power loop inductance, which is including the bypass capacitor to the high side FET, then the low side FET, and back to the bypass capacitor. And then we have the gate loop inductance. There are two circuits for each gate loop. One is for the turn-on, which is including the bypass capacitor for the gate driver. And the other circuit is for the turn-off, which is just shorting the gate to the ground, to the return terminal. So the effect of the common source inductance is as a feedback on the gate drive circuit. The rate of change of the current in the device, the DI/dt, is causing a drop in the common source inductance, and this drop is subtracting from the drive from the gate driver, and it's reducing the drive current to the gate and slowing down the transition of the current. And this can be seen, the effect can be seen on the power loss, which is increasing quickly with the increase of the common source inductance. Even 100 or 200 picohenry are already providing worse performance, worse efficiency for the converter. Regarding the power loop inductance, the effect is to increase the ringing on the switching node. So if you have 1 nanohenry of loop inductance, in this example, you can see a 70% overshoot, and this is the waveform. If you optimize the layout down to 0.4 nanohenry of inductance, the overshoot is reduced a lot, and also the ringing is minimized. And the effect of this is worse EMI, higher voltage stress on the device, and also can be the circuit can be more susceptible to parasitic oscillations, and so including the gate circuit, and be damaged by this. So if you plot the effect of the common source inductance on the losses and the effect of the loop inductance on the losses, you see the common source inductance is what needs really to be minimized. On the gate loop, you have a resonance circuit in the gate, which is formed by the inductance of the layout and the parasitic input capacitance of the device, and the gate resistor is added to damp the overshoot of this resonant circuit for the turn-on transition to stay below the maximum VGS rating of the GaN FET. For the turn-on, the ring needs to stay below the threshold voltage to avoid parasitic turn-on. So if you increase the gate inductance, the effect is you need to increase also the damping resistor to keep those ringings below, those overshoots below threshold. And by increasing the resistance, you slow down the transitions, and you increase the losses, the switching losses of the circuit. So let's have a look to the most commonly used layouts. So this is called lateral layout, is very popular, and all the devices are on one side. The power loop is developed on the top layer. Usually in the first inner layer, there is a ground plane. Then we have the external vertical layout. It's also very popular if you can use two side components. So you have the bypass capacitors on the other side of the PCB, and the power FETs on the top side of the PCB. And then this is the internal vertical layout. So you have all the devices on the top layer in line. So low side FET, high side FET, bypass capacitors. And the return path is in the first inner layer of the PCB. So in this example, we used a 4-layer PCB. How can I evaluate which is the layout with the minimum inductance? So as a matter of fact, the approximate equation for estimating the inductance of a path and its return, it's the magnetic permeability by its length, by the thickness, and divided by the width of the path. So a wider and shorter path with very small thickness between the going current and the return current it's minimizing, has a lower inductance than a long and a narrow path. So applying this to the previous layouts, we can compare an example. The lateral layout has a pretty wide, a pretty large thickness. So the area of the loop is pretty large, and it should have the worst case inductance, but this is mitigated by the ground plane on the first inner layer, which is creating an opposite current, canceling some of the flux and reducing the inductance. So in the lateral layout, you start, let's say, from 1 nanohenry, and then you go up if the insulation thickness between the first two layers is increased. In the external vertical layout, this is very dependent on the thickness of the PCB. And you can see the internal vertical layout is providing the minimum amount of parasitic inductance. So with 4 mils of insulation, you go down to less than 0.4 nanohenry. So this is the layout which we recommend to minimize the inductance. So how to design a low inductance layout? First of all, the components are placed on a vertical and as close as possible, so to keep this distance as short as possible. Many vias are used in parallel, and they are placed as close as possible to the innermost connection in order to shorten the path to the first inner layer, and keep this distance to a minimum. Then the insulation thickness is kept to the minimum amount required for the blocking voltage that is in the circuit. It's typically 0.1 millimeter for up to 100 volt and 0.2 millimeter up to 200 volt. And then the vias connection are spread to create a wide path, and also multiple bypass capacitors are used to create a wide return path for the currents. And it is worth to note that the first inner layer is focusing on the return path of the switching edges. So it doesn't need to carry all the current, DC current from the converter, but it needs to be designed with the focus on the switching edges and to minimize the inductance. As an alternate configuration for the internal vertical layout, you can place the bypass capacitors close to the low side FETs, and this is optimizing the cooling of the cooling through the PCB of the high side FETs. And in this case, the first inner layer is the input voltage of the half bridge. The other option is to place the capacitors between the high side and the low side FET. In this case, the first inner layer is the switching node, and this has two advantages. The heat generated by the two FETs is spread more evenly on the PCB because the FETs are more spaced, and also the switching node is buried on an inner layer. In this case, it's partially buried, but depending on the if you are using via simple, it can be fully buried in an inner layer, and this is very beneficial for shielding against radiated EMI. Regarding the gate connection, the same concept is applied. So you have the path from the gate driver to the gate terminal of the FET And in the first inner layer, you need to have the return polygon, which is always connected to the source of the FET. So in this case, the high side FET has the switching node as a return path of the gate driver, and in the low side FET, there is the ground as a return polygon for the low side gate driver. And this connection is returning the gate currents to the gate driver. Also, it is worth to note that the gate drive currents are mostly horizontal, while the power loop currents are mostly vertical. So this orthogonality is reducing the common source inductance to a minimum. So to clarify how to connect the gate driver to the FET, this is a common mistake that is made. So only this pad is used to connect to the gate driver and is not connected to the remaining source pads. And this is not proper. So as rules, all the source pads of EPC GaN FETs needs to be connected together. And in the same polygon, those two vias are placed near to the gate driver and its return, and this is working as a Kelvin connection between the gate driver and the power device. As final tips, priorities on the layout for the switch in the circuit. So if it is back, the switch is the high side, so that is critical. If it is a boost, the switch is in the low side. So the priority needs to be given to the switch FET. Smaller capacitors in large numbers can be used to close the power loop locally. So those are what we call the high frequency capacitors, and they need to deal only with the switching edges. Larger capacitors can be placed, but it is less critical. They need to deal with the ripple currents at the switching frequency. As an advice, I've seen a lot of components in the close to the gate of the FET that are working at low frequency or DC, and those components can be placed away from the gate and keeping only the critical components in the close vicinity of our devices. So gate resistors, so those there are dealing with the switching edges. And then it's important to start with the right footprints for our components. So as EPC, we provide Altium and KiCad libraries, and we have a reference footprint drawings in the datasheet. And also the silk screen, it's important. We advise to do not surround the component with a plain box of silk screen, because it's causing worse removal of the flux when you clean the boards, or can trap the flux under the device. So as examples, we have one half bridge with the EPC 2088, and let's say one of those gate drivers, which are very popular, and they are pin-to-pin compatible. So this is the view from the top side, and this is the schematic. So we have multiple bypass capacitors for the power loop, and we have bypass capacitor for the 5 volt, which is powering the low side of the gate driver. The high side of the gate driver is powered by a bootstrap. So this is the bootstrap capacitor. And then we have the gate resistors, and very important and often it's forgotten, we have an input filter to filter out some of the noise that can couple to the inputs of the gate driver, and this needs to be as close as possible to the input pins of the gate driver. So let's have a look to the most common mistakes in a layout for this circuit. So pad 2 of the component in this case has been used only as a Kelvin connection for the return of the gate driver. So we have the gate driver here. This is the turn on path. This is the turn off path. This is the gate terminal of the device. And this is the return. So as you can see, pad 2 is only connected to the gate driver return. Thin tracks for the gate signals have been used, and this is increasing the inductance. The gate drive return is routed only on the top layer, and all the high side section of the gate driver is routed on top of the ground polygon. Here it is. So this is increasing the capacitance between the gate and the ground is in AC is connected to the drain of the high side FET by the bypass capacitor. So basically, this overimposition of the gate circuit to the ground for the high side device is increasing the drain to gate capacitance, and it can also cause parasitic oscillation of the FET because of this increased capacitance. So how to fix those issues? Pad 2 needs to be always connected to the other source pads, as in this case. And those two vias are the Kelvin connection for the gate driver. And those are common to the power loop and the gate loop. Then you can increase the width of the tracks for the gate. And very important, in the inner layer 1, you need to have the return path for the gate driver. So in this case, this added polygon is connected to the switching node and is used as a return reference plane for the gate drive signals. So in the power loop, what can be improved? In this case, you can see added vias in pad, and those vias are creating voids that are interrupting the return ground polygon. And this is increasing the inductance of the power loop. So as a first iteration, we remove those vias and we place those vias which are connecting the input bus to the drain of the FET upwards. But those vias, they are not required to be here. They can be placed on the sides to keep the return polygon even less interrupted. And also the bypass capacitors can, in this case, be moved closer to the FETs, and together with their return, their ground vias, and this is shortening the overall length of the circuit. And this is the final result. Actually, those capacitors can be moved farther down. As an example for paralleling two FETs for a DC-DC, so we have the same circuit, but we added two extra FETs in parallel, and to be noted, they need to have their own gate resistors. So each FET needs ideally a turn-on resistor and a turn-off resistor. We added some more high-frequency capacitors, and as per the gate driver, the schematic is the same. So what we suggest is to lay out a symmetrical design. So it's more two parallel half bridges with a common gate driver more than two parallel FET devices. So as you can see, in this example, we prioritize the high side FET with the hypothesis of a buck converter. So we have used the inner layer one for the gate return of the high side and for the power loop return, and also for some low side gate drive routing. So this is the inner layer one. You can see this polygon is used as a return path for the gate drive signals to the high side FETs. And then you can see the return from the low side FET ground up to the bypass capacitors. The third inner layer can be used for low frequency, high current paths. So switching node from the devices to the output inductor, the ground, and the input voltage. This is the example. Last example with QFN devices with middle capacitors and barrier switching node. So we have QFN FETs with as many vias in pad as we could fit, and we could fit 48 vias in pad. Then we have high frequency capacitors between the high side FET and the low side FET. We have the medium frequency or bulk capacitors a little bit farther away because they are less critical. And on top, we have the gate driver, high side and low side. So in this case, we start from the high side, from the bypass capacitors, from the positive voltage on the high side capacitor. We connect to the drain of the high side FET. Then from the source of the high side FET, we connect to the, in the first inner layer, we connect to the drain of the low side FET. And then we go back on the top side and we return the currents from the source of the low side FET to the bypass capacitors ground. And as you can see, this is a very short path, very wide, and it can provide a really low amount of parasitic inductance. And regarding the gate drive, it's worth to note the high side gate drive circuit up here, including the bootstrap capacitor. So basically, this is the bootstrap diode. All of this circuit is laid out on the switching node, which is in the inner layer. And this is working as a return path for the ground drive current, the gate drive currents. Okay, so let's have an overview about rule of thumbs for estimating the parasitics in a PCB. So it is worth to note that both the resistance and the inductance are not related to the absolute dimension of the tracks, but they are related to the shape of the tracks. So in case of the resistance, you can define resistance per square, and with 1 ounce copper is about 700 microohm, with 2 ounce copper is 350 microohm. Regarding parasitic inductance, you can define an inductance per square in this configuration. So when you have a track and you have a reference plane as a return under the track, and the insulation between the track and the return is T, you can define the inductance per square as about 130 picohenry per square if the thickness of the insulation is 0.1 millimeter, or 260 picohenry if it is 0.2 millimeter. And regarding with the same configuration, the capacitance is depending on the area of the track, and it's about 40 picofarad per square centimeter or 20 picofarad per square centimeter. Regarding vias, we recommend to use vias in pad plated over, which are IPC 4761 type 7. So those vias are plugged with epoxy. They are plated over with copper, and then you can have the surface finish, which we recommend to use ENIC. And so this kind of via can be placed below the pads of the components, both the GaN FETs and the passive components and the ICs. And such a via has about 2 million resistance and thermally 300 degree per watt. The diameter of the hole, it's 0.2 millimeter, the plating thickness 20 micron, typical for IPC class 2, and the length of the via is 1.5 millimeter. So it gives a significant parasitic so the advice is keep as short as possible by using the topmost layers for the highest critical paths. Regarding inductance, it's hard to define the inductance of a single via. It depends on the configuration of the nearby vias of the return currents. But we can think about around 1 nanohenry inductance. It depends on the placement of the via with regards to the pad of the component. It depends on the diameter and the length of the via. So keep it short, keep vias short. And if you can use vias in pad, this is a way to reduce the inductance of the connection to the inner layers of the PCB, and even 2 vias is better. Regarding how to use vias with our devices, let's start with the easiest one. Is the QFN. We have 0.85 millimeter pitch. This is allowing us to use 0.2 millimeter drill, 0.35, 0.4 millimeter annular ring via, so up to 2 ounce copper on the outer layers. You can use 0.5 millimeter annular ring on inner layers to use up to 4 ounce copper. And in general, up to 0.25 millimeter drill and 0.5 millimeter annular ring is possible with our QFN device. Then we go to the next level, chip scale package with 0.5 millimeter pitch, like EPC 2204, EPC 2619, EPC 2218. The goal is to have at least 7 mils of creepage copper to copper, and in this case, you either remove the vias from the drain or from the source, or you place them in a zigzag way in order to make more room for them. Or the other option is to use smaller vias, which are usually more expensive. With our most difficult device to lay out, chip scale package with 0.4 millimeter pitch, like the EPC 2206, the situation is not easy to solve, so you can place vias only in those positions as shown in this picture. Okay, let's have now a final look at what is changing if you are laying out a motor drive and not a DC-DC converter. So what is the main difference between motor drive and a DC-DC converter? Basically, motor drive is switching at lower frequency than a DC-DC converter. So DC-DC, we go definitely above 200 kilohertz up to few megahertz. Motor drive, we go like tens of kilohertz up to 100 or 200 kilohertz. The rate of change of the current is lower in the motor drive. Current transition time is about 10 times longer. DVDT is 10 times smaller in motor drive, so voltage transition time is about 10 times longer. That time, while it is minimized for DC-DC converters to improve the efficiency, with motor drive, usually we go from 20 to 100 nanoseconds of that time. And usually motor drive, the switching losses contribution is smaller than for DC-DC converters. So this said, we can shift the priorities for motor drives compared to DC-DC converters. So let's start from the local high-frequency capacitors. So those are usually less critical. In some cases, they might be omitted. And interleaving the bus and ground layers will offer enough distributed capacitance to keep a clean switching. And also, this is thanks to the slower switching that can be obtained by increasing the gate resistors and increasing the switching times. The medium frequency and bulk capacitors, their placement is less critical to the switching, so they might be placed where it is convenient for the design, but we need to consider they carry significant ripple currents, so they still need to be in a low resistance path. And for motor drive, capacitors can be placed in the opposite side of the PCB of the FETs. So external vertical layout can be used for motor drive. And sometimes this is the most practical layout that can be used. It is important to distribute gate signals, shielding them with their source return. This is still mandatory to avoid self-oscillation or false turn-on due to the poor layout of the gate. And especially in case of parallel devices used for motor drive. For motor drive, we can simplify the approach for paralleling the devices. So the gate driver is on the left. This example is taken from the EPC 9186 board. So the low side FETs are on the top, the high side FET are here. We have the bus voltage, switching node, and ground. So how did we lay out the gate drive for this board? Basically, from the gate driver, we used an inner layer to bring the turn on and turn off gate track signals. And we placed the return polygons both on top and on bottom of those tracks to shield them and to reduce the parasitic inductance of the gate loop. It is worth to note that the power loop currents are vertical and the gate loop currents are horizontal, and this is effectively reducing the common source inductance. And also those vias local to each of the GaN FET are the Kelvin connection for the gate driver. So further tips, it is advised to use a lot of vias. So if you stitch layers between them, you create alternate paths and you reduce the PCB resistance. Stackup is very important. And we suggest to use heavy copper PCBs, so 6 to 10 layers, 2 ounce outer copper and 3-4 ounce inner copper. This is an example of Stackup, so 8 layers, 2 ounce 442 and 10 symmetrical. And you can use the first 3 layers for the high current paths like the switching node, the 2 ounce layers in the middle as signal layers, and the 4 ounce copper in the bottom part of the PCB as additional DC current paths for ground and bus distribution. Then it's needed to avoid to cut polygons with tracks. So in this example, you have this layer which is the copper polygon is interrupted by routing of signal tracks. Those tracks have been moved to another layer and the integrity of the copper polygon is restored. It is advised to use PCB design tools that are able to estimate the resistance, the voltage drop, and the current density in order to discover bottlenecks and optimize the layout. And also, the shifting priority is you need to optimize the high current tracks. So basically, the path between the bus voltage, the phase output to the motor, and the back to the ground. And the low inductance power loop can be moved to a lower priority because of the slower switching. So in this example, this needs to be minimized. The path from input voltage to phase back to ground. So to obtain as low as possible DC resistance in the copper of the PCB, you can think to repeat all the same polygons in all layers. So in this case, we have the low side FET and high side FET. The reference board is the EPC 91200. You have ground on top, switching node in the middle, bus voltage in the bottom, and those copper polygons are repeated in the first few layers to parallel them and to keep also the vias connecting them as short as possible. With the exception of one, which is still needed for the power loop retard. So this one can be an example in the third inner layer, but can be also moved further down to minimize the length of the vias and to reduce the DC resistance. Okay, we are almost over. So as a summary, we discussed the three layout parasitic inductances, common source, which is the most critical, power loop inductance, and gate loop inductance. We were showing the best layout practices and designs. Internal vertical is recommended. For parallel FETs, for DC-DC converters, it is recommended to parallel the half bridges. This is the concept. Then we provided some guidance on the PCB design with our FETs. And regarding motor drive, the priority is from optimizing the low inductances of the switching loop. The priority is minimize the DC resistance from the bus connectors to the phase connectors and back to the ground connectors. Okay, we have much more material online, so the presentation is over. Thank you for your time, and apologize again for the network drop we had.
All right, thank you, Tiziano, and thanks everybody. So we're going to start answering some of the questions that have been submitted during the presentation. As a reminder, you can still submit questions in the Q&A feature at the bottom of the screen. So Tiziano, the first question we have is, how does loop inductance cause increased power dissipation?
Let's go to the slide. This one, okay. So the higher dissipation is due to the bouncing energy between the output capacitance of the device and the bypass capacitors. So these overshoots. So this is bouncing energy between the output capacitance of the device, the parasitic inductance of the power loop, and this is causing additional currents that are causing losses. This is one factor. The other factor is you can have higher power dissipation in the overlap interval of the switching edge because of the higher voltage that is reached by the device.
Okay, thank you. Is there any paper for calculating the loop inductance?
I believe that they are. I don't have any on top of my mind, but this is basic. There are very old papers to estimate the loop inductance from geometrical properties of the design. I mean, this is I mean, I cannot remind the name of the author, but there are very famous old papers on the topic. And but nowadays maybe it's more useful to go into finite element modeling, which is not trivial, but it's it can be used. I mean, the very simple rule of thumb I provided in this webinar for the estimation of the parasitic inductance is this one, but it's limited to rectangles basically, which is almost always the case, but not always.
How does the overlap between the switch node and the P ground influence this circuit if the first inner layer is the return path of the power loop?
Let's go on the slide. Okay, I think this is the one. Okay. So basically, this is the I side gate drive circuit, and the currents that are going to the gate of the device and are returning from the source of the device, in this case, are just returning through this top layer path. So one first effect to do not have a return polygon connected to the switching node on the inner layer 1 is the gate loop inductance is increased a lot, because it's the same difference between the lateral layout and the internal lateral layout. With the difference that here you don't even have the you actually have the ground return plane to mitigate the effect, but the effect is to increase the loop inductance of the gate circuit. The other effect, which is even more critical, especially with the smaller devices we have, this is adding a significant amount of parasitic capacitance between the gate and the drain of the device. Let's not forget the ground is connected to the drain through the bypass capacitor. So there is, in AC, the ground is connected to the drain of the device. And this is adding Miller capacitance. And since our devices have gate to drain capacitance in the order of few picofarads or even less, we have devices with 0.1, 0.2, 0.3 picofarad of gate to drain capacitance. In that cases, the additional external gate to drain capacitance due to this poor layout can lead to parasitic oscillation and destruction of the FETs. It's turning the circuit into an Hartley oscillator. So with the power loop inductance, the gate loop inductance, and the gate to drain capacitance, this is easily becoming an oscillator, and that is destroying the devices, and it's very unpredictable. You might have a marginal situation where this oscillation is happening only for a limited range of the bus voltage, and so it's very tricky. And so this is really the most critical thing, and the mistake you really have to avoid.
Okay. Regarding the via placement, is it better to have the vias directly on the footprint or close but not directly on top of the footprint?
It's better to have the vias in the footprint, in the pads, if there is space to do that. It's highly recommended to have vias in pad. Vias in pad are good for reducing the inductances to connect better to the inner layers, to reduce the resistance, and also to improve the thermal transfer from the device to the inner layers of the PCB. So you can have a reduction of the temperature increase on the device if you are using PCB only cooling by a factor of 2 if you are using vias in pad. So if there is space and if the features of the vias are allowed for the PCB technology and PCB manufacturer, highly recommended to use vias in pad. And they don't cost much more than vias out of pads. It's a technological adder, but it's also helping to make your design smaller. So most likely use less PCB.
What do you recommend when you want to use two separated drivers? How can you optimize the layout in that case?
Two separate drivers is even easier than to use an half bridge gate driver. So where we have the example. Okay, we have the example of the. Okay. So if you have two separated gate drivers, you have one for the high side and one for the low side. Once the input signals are connected properly and they don't pick up noise to both of the single gate drivers, then I don't see any particular issue. And you can use the same rules for this half bridge gate driver example, but you have more flexibility regarding the placement of the two gate drivers.
Do you have any recommendations for VDS DSAT sensing?
VDS DSAT sensing is very difficult. It happens at very large currents. It can be used, but due to the fact that most of our devices have very low RDS(on), the tripping point for the VDS sensing can be very low, so in the order of 100 millivolt or 200 millivolt. So you really need a low noise sensing and a good solution for the blanking interval after the switching. So we don't have a proven solution so far. This is the final answer. Some customer has done it with more or less success, but it's not an easy task.
Okay. Should the signal ground containing the sensors and PWM signals be the same ground as the power ground, totally isolated from each other, or a small net tie 0 ohm resistor connecting between them?
In this case, the interface is the gate driver, if we limit to the driving circuit. So the ideal connection point between the power ground and the control ground is in the close vicinity of the tracks that are bringing the PWM signals to the gate driver. And depending on the design, it can work both with the separated ground between the controller and the power loop, but it can also work with a single ground. So it's but usually the separation between the signal ground and the power ground is recommended.
Okay. Why is it recommended a turn on and turn off resistor?
Yeah, we recommend for most of the applications gate driver with split outputs. So one output with pull up to turn on the FET, and one output with pull down to turn off the FET. And in this case, you can optimize the turn on resistor differently from the turn off resistor. In example, you might want to slow down the turn on by increasing the turn on resistor, but keep a good rejection of the self-induced turn on by keeping the turn off resistor of much lower value. If you have a gate driver with a single output, we recommend to use just a single resistor, since turn off is less critical. You are not adding significant losses if you increase the turn off resistor. If the layout is done properly, the self-induced turn on is not a problem.
Can turn off diodes be used if the gate driver does not have an independent low slash pull down output?
Yes and no. Recommendation is to use just a single resistor to be used as both turn on and turn off, as I was saying before. If you add components in the gate, there is a chance that the improvements you can have to have a diode and an additional resistor to speed up the turn off are compensated, let's say, by the additional parasitic that you are adding in the gate circuit. So basically, most of the times it's not worth to use an additional speed up diode and resistor for the turn off.
Okay. If I want to have a negative drive voltage, which gate driver is suggested, such as +5 volts, -3 volts?
First question, why do you want negative voltage? It is not helpful. It can increase the freewheeling losses because it's increasing the VSD in freewheeling of the FET. And it's not needed once you have a good layout. So this is why we recommend, and we have only gate drivers recommended which are not supporting negative voltage drive. But of course, you can arrange a solution with a standard gate driver providing a small negative offset, but it's not really recommended. It's not needed. So the best solution is to do not have the problem to solve. In this case, we are fine with 0 volt turn off.
You might have already answered this, but I'm going to, just to be sure, when designing a high current system utilizing multiple parallel EPC GaN to increase efficiency, does each of the EPC GaN require its own gate driver, or can they share the gate drive from a single gate driver?
No, if you use one gate driver for each FET, you have a chance of mismatch in propagation delays between the several gate drivers, and that is not helping to equalize the losses during switching. So the best option is to use a single gate driver driving all the parallel FETs. Each FET needs to have its own gate resistors, and so avoid to parallel the gate directly between the devices. And we have seen up to 4 parallel devices. We can have a good solution to share a single gate driver among 4 parallel devices by paralleling 4 half bridges. above 4 parallel devices for DC-DC converters, we recommend to use multi-phase approach. So if you can reach the current you need with 4 parallel devices, you can find a good layout. If you need more than 4 parallel devices, it's better to increase the number of phases. This is for DC-DC converters. For motor drives, we have designs with up to 12 parallel devices, but that is another story. The switching speed in this case is much slower, is kept very like 10 times slower than DC-DC, and the layout is less critical, as we were showing in the design example.
How do you do a vertical commutation loop when you are using bottom side cooled devices with cooling through the board?
How do you do vertical when you are cooling through the board? Ah, okay. So why do you want a vertical commutation loop? So basically to put the capacitors on the bottom side. So place the capacitors on the bottom side and dissipate from the bottom side. You have to move away the capacitors, and the best option is move to an internal lateral layout.
Regarding the via, why fill it with epoxy?
That's standard production manufacturing step. So before plating them, you need to have them filled.
Okay.
This is the slide. Okay. So manufacturing process for a via, you drill the hole. There is the electrochemical process to deposit the sides of the via. Then you can fill the via with epoxy, and with the electrochemical process plate over in order to have a flush copper surface. The other option, so you have to fill the hole with something. Either it is epoxy, and this is a very cheap process, or you can fill with copper, and that is a very expensive kind of via, but it's very effective for lowering the RDS(on) and the thermal resistance from one side to the other of the PCB.
Okay. Is it also a good practice to place a footprint for an additional gate capacitor for tuning purposes like with MOSFETs, or is it something to avoid absolutely? This is specifically for a motor drive application.
Yeah, you can place an O4 O2, something like that, size capacitor between gate and source that can be used for debugging purposes. For tuning the turn on and turn off speed, we do not recommend to add capacitance to the gate, but just to increase the gate resistance.
Okay. Any recommendations when routing both A ground and P ground traces to a motor drive FET half bridge for internal connection within the device?
Can you read it again? Sorry, René.
Sure. Any recommendation when routing both A ground and P ground traces to a motor drive FET half bridge for internal connection within the device?
Not clear. So
Okay, maybe we can, whoever asked that question can send a follow-up just directly
yeah, maybe we can
to
follow
us.
up later. Yeah, it's
Okay.
not clear the question.
Okay. Do you recommend any TVS diodes for gate drivers?
To protect the gate, No, we don't recommend TVS diodes.
Okay. An extension question regarding the turn-on diode. Is it a good practice to use Zener diode across the gate resistor for additional protection?
It's very difficult to protect the gate with the Zener diode because it needs to be placed with a very low parasitics, and so it's not very effective. It is, I mean, the first line of action is tune the gate resistors to avoid excessive overshoot. And then, of course, you can think to use Zener diode, but the response time is not always enough to provide a full protection of the gate.
So unfortunately, we have a hard stop here. If we didn't get to your question, please, well, I think unless you submitted it anonymously, we'll reach out to you and answer it. If you did submit it anonymously, please submit it to info@epc-co.com and we'll get them answered as well. And if you have any other questions, please feel free to reach out to us. Thank you, Tiziano. Thank you, Rolf, and everyone have a great day.
Thank you.
All right, thank you.
Thank you. Enjoy your day.
Thank you. Bye.